Hello everyone and welcome to my channel Ghiloo once again. So in this video I'll be continuing from question number 13 onwards of the chapter Continuity and Differentiability. So without any further delay, let's get started. So in question number 13 we have a function that is defined by the following definition. We need to show whether it is a continuous function or not. So the basic fundamentals lie exactly the same. Here the definition of function breaks at 1, and before 1 and after 1 the function has a value that implies a polynomial expression. So we know that any polynomial expressions fx which are polynomial in nature are always continuous in a specified domain. Now here for x greater than 1 we have the definition as x minus 5, so obviously for x greater than 1 it is continuous. Similarly for x less than or equal to 1 we have for x less than 1 it is x plus 5. The definition breaks at x equal to 1, so our vulnerable point for checking out this continuity is x equal to 1. So let us check it at x equal to 1. So given f of x is equal to x plus 5. Now since for x less than 1 and x greater than 1 the expression are polynomial respectively, so it is continuous throughout for this domain. So this is just a new expression for writing. You can write it in this way also. That means if x is continuous for all x belongs to minus infinity to 1, these are in open brackets, union 1 to infinity. That exactly means 1 subtracted from the set of all real numbers. So since x equal to 1 is the point, since x equal to 1 is the point where the definition of f of x changes, we need to check continuity at x equal to 1. So for x equal to 1, LHL, the left hand limit is limit of x tends to 1 minus f of x. Now just for x less than 1 we have the definition to be x plus 5. That gives us 1 plus 5 is equal to 6. Now RHL is limit of x tends to 1 plus f of x. That means x is from right hand side, and just for x greater than 1 we have the function to be x minus 5, and that gives us 1 minus 5 which is minus 4. And f of 1 is equal to obviously 1 plus 5, that is equal to 6. So therefore LHL not equal to RHL, hence f of x is discontinuous at x equal to 1. This was it, a very simple question. Now coming to the next question. In the same way we got question number 14, 15 and 16. We need to discuss the continuity of the function f where the functions are defined by the following. So see, I won't be writing the same steps again and again. I'll be just concluding by here just by seeing whether it is continuous or not. See, I can follow a different approach here as well. We can write like this. See, if you follow the graphical method, let us start with question number 14 for that. It is f of x equal to 3. Let us draw a graph for question number 14. For x belonging to 0 to 1, suppose this is 0, 1, 2, 3, and for that we have the function defined up to 10. So let us get the definition up to here. So for 0 to 1 we have value as 3. From 1 to 3 we have the value as 4. You can see it because here both 1 and 3 are open. See, so we are not including 1 and 2 here, 1 and 3 here. And from 3 to 10, from 3 to 10 we have the value as 5. So you can clearly see the point of discontinuities of the function. If you can just visualize, you can see that the definition starts from 0 and ends to 10. So let us check the continuity. See, from 0 to 1 you need not to lift any pen. So from 0 to 1 it is continuous. So x is continuous for x belongs to 0 to 1, but you can see that the continuity is lost at this point because you need to lift your pen. So x is discontinuous for x equal to 1. I have given an open bracket because x is not yet 1. So here from 0 to just up to 1, we need not to lift any pen. So it is continuous here. Once again from 1 to 3, it is continuous as you can clearly see. And from 3 to 10, it is continuous, completely continuous. So x is discontinuous where the definition breaks. So the viable point of discontinuities are 1 and 3 because there is where the definition breaks, and we can see that for each of the following cases we need to lift pen. So for x equal to 1 and 3, it is discontinuous. For all the other values from 0 to 10 except 1 and 3, x is continuous. That's it. And similarly is the case of question number 15. If you know the very basics of coordinate geometry, which I would anyway assume you know, we have for x less than 0, the function is 2x. Now you know that the graph of 2x will be somewhat like this with a slope 2. So for x less than 0, that means 0 is not included, we have the graph to be like this. So this is 2x. For x belonging to 0 to 1, we have the value as 0. That means this is 0, this is 1, let us suppose. So this entire value is going to be 0. Okay, and for x greater than 1, we have it as 4x. So the function is 4x for x greater than 1. So if x is just equal to 1, the value of the function should be 4. So it's where it starts. From 4 it starts with a slope 4. This is the graph of the function. Now you can clearly see that the viable points of discontinuity, which is vulnerable, are 0 and 1 because these are only the 2 points where the definition of function breaks. But for either of the cases, you can see here for x equal to 0, you can see that there is no discontinuity because the limit exists both for the right hand side of 0 and the left hand side of 0. You can clearly see that the value approaches to 1, which is defined. So at x equal to 0, the value of the function is 0. It is defined and it is continuous. But you can see that you need to lift pen for drawing after 1. So the point 1 is discontinuous. So the function is continuous at all points except at x equal to 1. Similarly in question number 16, if you see that for x less than or equal to minus 1, we have the value to be minus 2. This is, let us suppose, minus 2. 2x, if minus 1, x is greater than minus 1 and less than or equal to 1. So this would be 1, let us suppose. It is 2x once again. So for 2x, you know that the graph would go like this. And from there we have, see, at 1 the value will be 2, and from there for x greater than 1 we have the value as 2. Now you can clearly see that the function is continuous throughout the domain because we need not to lift pen at any time. Where the function, the definition closed, the definition of another function opened at the same point, and so is the case for both the points where the continuity was vulnerable to be checked. So here we can conclude that the function is continuous at all points. In this way you can write it yourself. You can take any method you want, but if you are following the graphical method, please ensure to write each of the things very properly. You have to be precise, to the point, and you need to explain to the examiner that you are well informed about this. So I hope that you have no problem. If you have any kind of problem, please feel free to use the comment section. We'll be meeting in the next video where I'll be discussing the next set of questions. Thank you very much for watching.